Okay. Hello everyone. My name is Hiroshi Watanabe from Japan. And this is the very last talk, so that means I don't have to take care of time, right? So I'm from Japan, and I have never used the Blue Waters. But I'm a user of the K computer, which is the largest computer in Japan. So I came here to show you some results that are obtained by using the K computer. And let me introduce the K computer briefly. This one, okay. This red one is a K computer. This is just a Fujitsu machine, and it is a homogeneous system. That means we don't have any accelerator. Well, that would be nice. And CPU is a Spark chip. With one CPU has 8 CPU cores, and with uniform memory access. We don't have to take care of the NUMA. And one node consists of one CPU, and the total system consists of the 83,000 nodes. It gives you the 10 petaflops. And currently it's ranked as the fourth as the top 500. That means if you perform HPA on Blue Waters, you will rank here. If you have time, please try it. And using K computer, I'm studying the gas liquid multiphase flow. Suppose we have some hot pipe flowing water, and if the pipe is hot enough, there are many bubbles appears. And this kind of system is very important, especially in a cooling system. And if you have the trouble in a cooling system of the nuclear power plant, you may know what happened in Japan. And this kind of system is very difficult because this is typical multi-scale multi-physics problem. In a small scale, we have the phase transition. Larger scale, we have the macroscopic flow. And as for numerical problems, we have the moving annihilation and the creation of boundary due to the phase boundary. It makes it difficult to perform this kind of simulation. And usually people adopt hierarchical modeling to study this kind of things. That means divide a system, divide a problem into sub-problems by its scale, and assuming the different government equations for different scales, and calculate something, puts the parameter to the higher scale, and so on and so on. But in nature, there are no hierarchy, right? So there are only particles or molecules, interacting molecules, that's all. So if we have enough number of particles, we can reproduce these kind of complex phenomena just by assuming some particle interaction. This is a direct simulation approach. I will show you some examples. Here is the paper. If the temperature decreases, they will condense into liquid, and they try to minimize the surface area. Note that this is a molecular dynamics simulation. So after the temperature decrease, everything is time reversible. There are only Newton's equation in motion. So we don't take any care of the phase transition or the phase boundaries. Just they try to minimize the surface area spontaneously. This is a direct simulation approach. Okay, I will focus on bubble nucleations. And we have the theory for which can predict the nucleation rate of clusters. And what is the bubble nucleation and droplet nucleation is just a different side of the same phase transitions. This theory works well for droplet nuclei, but it fails for the bubble nuclei by the 10th order of magnitude. We don't know why yet. So I want to study this kind of things. And there are some difference between the droplet and bubbles. So to create bubbles, the bubble should push to the ambient liquid. So it requires additional work to create a bubble. And interaction between bubbles is very strong compared to the interaction between the clusters. Here is just a dilute gas, but here is the dense liquid. This is the main two difference. But it is very difficult to investigate this kind of, to calculate this kind of work directly in the simulation. So instead I try to perform the huge molecular dynamic simulation to infer the microscopic behavior from the macroscopic behavior. And the simulation method is just a simple molecular dynamics method with the short-range interactions. I use the truncated Lennard potentials. And for huge scale computations, sometimes OpenMP and NPI hybrid parallelization required, so I did it. And the general approach for the hybridization for the MD is to adapt domain decomposition for NPI and the loop decomposition for OpenMP. This is a hotspot of the molecular dynamic simulation. Just a double loop and for the interacting particles to calculate force, and we can write some directive of OpenMP here or here. But the problem is we have the conflicts on the right back of momenta because it could be happen that different particles can interact with the same particles, and we can resolve it. But most important thing is we have to treat simultaneization and thread parallelization simultaneously. This is nothing but a two-front war, which is always bad operation, bad strategy. So instead, we adopt the should-flat MPI approach. That means we adopt the domain decomposition both for intra and internal parallelization. So I use thread ID as a rank of the MPI, and just calculate its just like a flat MPI. And if you have the flat MPI code, it's very straightforward to implement the should flat MPI codes. And the memory locality is automatically satisfied, which is not related to K-computer because K-computer has a uniform memory access. And the most important thing is we have to take care only simultaneization as the hotspot because thread parallelization is performed at a higher level. And the demerit is, perhaps you may know that we cannot call the MPI function freely in a thread. So the communication becomes troublesome. So the process should be work as a post office. They gather the data and pack it and send it, and this guy distributes them or something like that. But it's a troublesome and bothersome, but it's not difficult. Just we can do it. So it's troublesome, but we did implement it. So and to utilize the K computer, simultaneization is very important. Perhaps you know the simultaneization to use SIMD instruction in something like that. And we find that the store operation is involving the indirect addressing is quite expensive for the K computer. This is a feature of the Spark chip. And okay, we give up the Newton's third law to avoid indirect storing, and then we have the computation becomes doubled, but the speed up is threefold. Then the total gain of speed is over 50%. It will be very nice, but the value of flux is just meaningless because we calculate double. And we perform the hand simultaneization. We find that compiler cannot generate the SIMD operation efficiently, so we perform the hand simultaneization, blah, 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 something like that. But, it's just messy, and we perform the hand unrolling for 4 times and software pipelining, something like that. But if you're interested in these kind of things, you can see the source code, which is online. And okay, we perform the benchmark on K computer. This is the details of K computer again. And we check the performance between the flat MPI and the hybrid. And for flat MPI case, we put the 8 processes on the node. And for hybrid case, we put the 1 process and 8 threads per node. And note that the computation assigned to each core are perfectly identical for both schemes because we just we adopt the should flat MPI. Okay, here is the benchmark result. This is the elapsed time, and here is the nodes. And this is just a weak scaling. So if we have the perfect scaling, this should be flat. And the red one is flat MPI, and blue one is hybrid one. So you can see the flat MPI is always better than the hybrid. And the largest one involving 3,000 billion particles or something like that. And its performance of the largest one is corresponds to the 1.76 petaflops, which corresponds to the 16 or 17% of the peak performance. But if we use adopt the flat MPI, it becomes about the 20 or something like that. Okay, it's nice, but perhaps you know the flat MPI is memory consuming. This is the memory usage between the hybrid and flat MPI, and you can see the memory usage is almost flat for the flat for hybrid, but we have some increase in the flat MPI, and this is memory usage per node. We can use only 12 gigabytes per node, but flat MPI use 3 gigabytes more than the hybrid calculation. So it's very huge. But at this point, 4,000 nodes, flat MPI uses 1 gigabyte more for hybrid runs. So it's not small, but it's acceptable. So I decided I make some hybrid codes, but I decided to use a flat MPI for production using the 4,000 nodes. Okay, here is the science. Just prepare the equilibrium liquid, and we perform the adiabatic expansions, just 2.5% on the side. And then the system becomes unstable. There are many bubbles appears, and larger bubbles becomes larger, smaller bubbles become smaller. This is known as Ostwald ripening behavior. And finally, the single bubble will be survived. And details of simulations as follows. I used 4,000 nodes of the K computer, which corresponds to the half petaflops. And parallelization is a simple domain decomposition without any load balancing. And total step is 1 million steps. And each run takes 24 hours. That means one run corresponds to 0.1 million node hours. And I take 10 different samples in temperature. Then it corresponds to 1 million node hours. This is the value assigned to this project. And here is some movies. Okay. After expansion, we have many bubbles. And okay, this guy will be winner. And this guy and this guy interact with each other without touching. So this guy is killed, and this guy will be killed. And this guy is a survivor. Yeah. And here is just a small calculation for visual, just for visibility. And this is a 1 petaflops calculation. Oops. There are many bubbles, but it's very hard to see what happened here. Okay. I rotate it. It's still hard to see. I also tried some ray tracing. This looks better. Okay. Anyway, we have some multi-bubble nuclei in the initial stage, and Ostwald ripening, and finally we have the single bubbles. Okay. And for larger one, we have something like that. And bubbles appears as a result of particle interactions, and Ostwald ripening is observed as a result of a bubble interaction. That means we have succeeded in the direct simulation of multi-scale, at least 2 scales we have. and multiphysics learning. And data I/O is very important. So this is the definition of bubbles. We divide the system into small cells like this, and a cells with density smaller than some threshold is defined to be a gas phase. And okay, this guy and the gas cells, and the neighboring gas phase is defined to be belongs to the same bubble. And data format, of course, we are performing the petaflop calculations, and the data could be a petabyte or something like that, but I don't want to treat the petabyte file, so I try to compress them. So a number of particles in a cell is stored as unsigned chunk. That means 1 byte. It is very nice because we don't have to take care of the byte order. Because the K computer is Sparksheet, it's a big endian, and the analysis machine is x86, it's a little endian. So we have to think about the byte order or use the HDF5 or something like that. It's a bothersome. But if we use the unsigned chunk, everything is okay. And a system is divided into the 33 million cells. It corresponds to just simply 33 megabytes per snapshot. I put the 1,000 frames per run. It gives you the 33 gigabytes per run. And in the total, this project gives just 300 gigabytes. It is reasonably small. Okay, obtains data. I calculate the bubble size distribution. This is 20 tera. The red one is the smallest calculation, 20 teraflops and something like that. And the larger one is 1 petaflops calculation at the same timing. You can see they share some physics, the same physics, but the red one is obviously the red one's accuracy is not is insufficient for further analysis. So we need at least 1 billion particles to study population dynamics with bubbles, which is needless to say, which is impossible without the petascale computers. And here is some physics. I will skip it, but we have the theory for oswald ripening. The prediction is just the total number of bubbles decreases, has the power of decrease, and the average of volumes has the power of increase, sharing its exponent. And this is the result. Number of bubbles has the power of decay, and average volume of bubbles has the power of increase, sharing the exponent as predicted. That means this theory works fine. This is the first calculation that's to confirm that this theory directly for the bubble nuclei. And for larger if the system becomes larger, then this scaling region becomes longer. If we perform the smaller system, we cannot have any scaling region. Again, we need field scale simulation. And with another new finding is the scaling exponent changed as the temperature increase, and this corresponds to the change in the bottleneck of the system. If the evaporation is the bottleneck, then it gives you the exponent 3/2. And if the diffusion is the bottleneck, it gives you the exponent is 1. That means we can infer the microscopic dynamics from the macroscopic behavior. Okay, let me summarize my talk. Anyway, we did physics. We did physics using petascale computers. This is highly non-trivial because there is a huge gap between the demonstration and doing physics. So using petascale computer itself is very difficult. So there is some jump to do some physics using a petascale computer. And towards exascale computing, we definitely need new language. So I use C++, but C++ is definitely unsuitable for HPC. I like C++, but compiler does not like it, especially since the compiler does not like C++. And the parallelization is very messy. You know, I use the library for MPI and the directive for OpenMP and the intrinsic functions of SIMD. That's enough. So And additionally, perhaps we can use Xeon Phi or GPU or using CUDA OpenCC or something like that. It's kind of nightmare. We definitely need some new, nice language. And our code are available online. And this is written in C++, and just like, this is a product code, but less than 5,000 lines. So I believe it's readable. So if we interested in just put the MDACP in Google, just put search. Thank you very much.